For our last little few lectures here, we're going to talk more about the universe and cosmology, from beginning to end, the universe. We kind of ended last couple lectures about talking about the cosmic background radiation, and the Cosmic Background Explorer satellites, part of NASA's Explorer series of satellites, which is a series of satellites that was started with the very first satellite launched, and the series, each one is called Explorer, and there's been dozens of them, several dozen, many dozen, so the Cosmic Background Explorer was one of these scientific satellites designed to study the cosmic background radiation. And we found that it was a virtual perfect fit for black body radiation of 2.725. Now, there are some variations in there. Early universe would not have been perfectly smooth. There would have been some parts a little bit warmer, a little bit cooler, because it would have been a little bit thicker, a little bit thinner. Where the universe was a little bit thicker, gravity would have been a little bit higher. It would have been pulling stuff together. The gravity would have pulled on the light, and actually would have looked a little bit cooler to us, because it would have been a little bit more redshifted. Where the universe was a little bit less thin, then it would have looked a little bit warmer. Okay, so these higher and lower densities were what originally gave us the voids and superclusters. And so that would manifest in the cosmic background radiation. So here we have a color plot, and the way this is going to work is I'm going to plot blue is 0 Kelvin, red is 4 Kelvin. And as it plots, that's the whole sky plotted on a projection here. You notice it's all one color. That means there's virtually no variation anywhere in the universe. So we're going to zoom in 2.724 Kelvin to 2.732 Kelvin, blue to red. And you notice there's variation here. Blue here, that's going to be a little bit cooler, red a little bit hotter. Okay, now really we already said what's happening here. That's because where it's red, where it's warmer up here, that's actually blue shifted. It's where it's blue and marked cooler down here, that's where it's red shifted. That's because of the motion of the Earth through the solar system, orbiting the sun, which is going around the galaxy through space. Okay, so all of that means we're heading in this direction away from that direction. And so if we subtract that, we can plot again between 2.724 Kelvin and 2.7252 Kelvin. Now we have this very tiny variation. The red line in the middle, ignore that. This is COBE data we're plotting, and that was interference from our own Milky Way. So this plot has the Milky Way across the center of the plot. This is what we call galactic projection. And so, but you do see regions here that are warmer and cooler. Okay, now that clumping eventually pulled stuff together to give rise to what we saw in the cosmic background radiation. So a fraction of the second after the Big Bang, we had a little bit of clumping that caused the variation, the background radiation that we see, and that eventually gives rise to walls and voids. Okay. So the question is, what about the size of those clumps? Do they really explain the walls and voids? And this is important because this relates to the flatness of the universe. If the universe is perfectly flat, the clumps look exactly the right size to correspond to walls and voids. If we have a closed universe, in other words, if we have spherical curvature, in other words, it's going to fall back in on itself, then the clumps are going to appear too big. If, on the other hand, the universe is open, hyperbolic, the clumps look too small. And so to measure that, NASA launched another mission. Now this one actually, instead of launching to space, interesting enough, was in a high altitude balloon that floated around the South Pole, called the Boomerang Mission, because it floated all the way around back to the starting point. And this is what it measured. And very carefully measuring in microwaves the entire sky, we realized that those variations actually come from sound waves, like sonic waves passing through the early universe. And they created the hot and cool regions that are in there. Those fluctuations are about a degree in size, and by measuring that, that helps us measure roughly the age of the universe. So these sonic variations, thick, thin, going through the universe, that would give us these clumps. Now, one of the things we discover is the clumps are exactly perfect size for a flat universe. By the way, if you could actually see microwaves, here on the left, this is what the sky would look like if you could actually see microwaves. Now, flat universe, as I said, there's like one way the universe can be flat, an infinite number of ways. It can be open, nearly an infinite number of ways. It can be closed. So statistically, this is very, very unlikely. The supernovae measurements, all the other measurements we make intersect with a universe right there. In fact, we have other models we do, so indicating all these models intersect in one spot, and that kind of means the universe is speeding up and slowing down, but it's perfectly flat. So there's a cosmological constant, there's dark energy involved, but the dark matter density is exactly right to make the universe flat. Statistically, this is like one of the most unlikely scenarios you can possibly imagine, and yet that's what we got. So these are relatively recent values here for these parameters. This is the density parameter for matter. Density parameter of 1 means perfectly flat universe. And what we have here is just barely off of 1, but how far off of 1 is within the statistical degree of uncertainty. So that's pretty close to 1. If it's any bit over 1, we are closed, but we'd be closed with constant acceleration because of the dark. Okay, your book presents this data right here, basically the same thing I just had, but with a few more things in there. So why is knowing the Hubble constant so important? Okay, it's important because that allows us to figure the age of the universe and what's going to happen in the future to the universe. Measuring the Hubble constant. Lemaitre was one of the first ones to measure it, Hubble shortly thereafter, and they got these incredibly huge values in there. Later astronomers started getting smaller values. Sandage and Tamanton got very small values. Generally, before 1996, values ranged between 50 and 100 kilometers per second per megaparsec. And now that's a factor of 2, which means a difference of factor of 2 in age of the universe. Hubble and Lemaitre's initial measurements were so high because the only galaxies that they could measure were the closest galaxies to us and the brightest galaxies, and they happened to be acting a little bit different than the average. Okay, Hubble telescope eventually started studying here, and they came up with about 72 kilometers per second per megaparsec. More accurate measurements came up with 73.2 kilometers per second per megaparsec in 2016. And these were looking at a variety of different features, different sort of things in the universe, plotting them out, finding the slope of the line, kind of like you did in lab, to measure. However, the Planck mission, another orbital mission similar to the COBE satellite, joint mission with the European Space Agency, also studied the Hubble constant. And they were measuring the variations in bright and dark in the cosmic background radiation. Fine-tuning those measurements allowed them to measure the exact Hubble constant. Now, what they came up with was a Hubble constant that was considerably lower than everybody else did. And so that changed kind of what they thought was proportions of matter and dark energy in the universe. came up with a little bit different age of the universe, 13.8 billion years, instead of the more commonly accepted 13.7 billion years. Okay. What is that difference? Well, other studies started looking into this, because now we had the Planck constants, which was supposed to be one of the most accurate measurements that were there, and then but the Hubble Space Telescope measured a little bit bigger numbers, and they were supposed to be the most accurate, and yet they started doing more and more measurements, and they found out that if you measure the Hubble one way, you get almost always the low value. If you measure it the other way, you almost get almost the high value. And so here are some measurements here of things that are in the universe, and those are the values they get, that they're more relatively high values. If you measure the background radiation and other sort of structures there, you get a lower value. And that's very, very consistent. And so there's a huge difference between which way you get. Now, the gravitational waves give something like in between, but like the range of uncertainty is like absolutely enormous right there. Okay. So that gives us a variety of issues. And we don't really understand why there's that variety of issues right there. What we don't understand is why one set of values give one thing, one set of values give another thing, and if you measure one type of thing, you always get low values. You measure another type of thing, you always get higher values. That says there's something very, very fundamental in there, and that's going to be something that we don't understand yet. Nobody understands that, and so that's something we're going to be studying later. Oh, actually, I guess not this semester, but that's something that astronomers are going to be studying, trying to figure out what the difference, because it does suggest there's an underlying difference. Now, the values are not vastly off, so we'll have to look at why they are somewhat different. What are we not taking into account? This is not enough difference to so radically change our view of the nature of the universe or the age of the universe. I mean, we're talking about a difference between 13.7 billion years and 13.8 billion years. This is not a huge difference right there. But it does indicate that we don't know everything yet. Our next topic, though, is to talk about the horizon problem and the flatness problem. So that'll be in the next video.